Alright, so now we're going to get into the other classification of compounds. So we're going to get into molecules. So they have covalent bonding. And so if you remember from before, these molecules are held together a little differently than the ionic compounds. So what they're held together by are shared electrons. And these are also known as covalent bonds. And so covalent because it uses the valence shell of both atoms to create an area where electrons are shared. So that's why it's called covalent bonds. And so the bond is going to equal 2 electrons. So what happens is each atom pitches in half and half on a bond. They each throw in 1 electron and they share 2 electrons together, 1 from each, to create the bond. So it's going to be 1 from each atom. So a bond is always between 2 atoms. And so an example of this, if you have hydrogen, it's going to have 1 valence electron. If I have another hydrogen, it's going to have 1 valence electron. So these are just 2 hydrogen atoms. And what happens is they'll each pitch their electron in, and then they share them between the 2, and they make the H2 molecule. So both electrons are shared in the middle. And what it does is it allows you to count the electrons in both valence shells. So this hydrogen has 2 electrons in the bond here. Both these electrons are in this hydrogen's valence shell, but they are also in this hydrogen's valence shell. So it lets them fill out their valence shells. So one way to do that is to become an anion and just take electrons, and the other way is to share electrons and accomplish the same goal. And we'll talk about how you know which one's going to happen when, and all those details in a little bit. But first, let's talk a little bit about these bonds some more. So there are 2 electrons being shared in between the atoms, and they're elastic, which means they're like a rubber band. So ionic compounds are like little balls that just stick together. That's it. There's not a lot of movement there, but chemical bonds are dynamic. They're very elastic. They're stretchy. Molecules have a lot of motion, and so there's all kinds of molecular motions that come into play, which is a big part of things that I studied when I was in graduate school, was using lasers to essentially probe that motion of a molecule and figure out what it's doing. So that's because they weren't like set in stone. Like it wasn't just 2 spheres stuck together. It's 2 atoms, but it's give and take, and they can move around, they can rotate, all kinds of stuff. And then the other thing is bonds are going to release energy when they're formed. And so here's an energy diagram for a chemical bond. And so on my y-axis here, I just have energy. Here's my 0 mark. And then this R is my bond length. So as R gets larger, the 2 nuclei get farther apart. And as it gets closer, they get closer together. And so this is the 0 mark where one would be completely inside of the other. And if you think like that doesn't seem reasonable, good instincts. That doesn't happen. So what we get is something that looks like this. Alright, and then at this lowest energy level here, lowest spot in the well, we get the average bond length. Because again, they're moving, and so there's a distance that's very stable, and it might move in a little bit, but then it's going to push out, and then it's going to get pulled back, and so you get this rubber banding effect. Now what happens if they get infinitely apart? Why do we go to 0? Well, that means they have no interaction. If they're infinitely far apart, they're just going about their business independently. They need to be a certain distance from each other to have a chemical bond. If you get them too far apart, the rubber band breaks. They're no longer elastic and stuck together. They are free to move about however they move about. And if you push them too close together, you start trying to push one inside the other, that's going to take an infinite amount of energy to be able to squeeze one atom inside of another. It's like trying to get, I don't know, like 4 people inside of a Kia or something. Like, it's impossible. You can't do it. There's not enough room. And so that's why we get this behavior. And so that's why we have a negative value. Because if they're at 0 energy at no interaction, if they're going to be favorable, they need to be less than 0 energy. So the energy drops. And so there's energy that's released in the form of heat or something like that. And so rearranging bonds, different bonds have different energy values. We'll talk about that later, but that's what drives a lot of chemical reactions for generating things like electricity or car, getting your car to move, is rearranging the types of bonds you have so that you get more energy out from the chemical process. So, these molecules do a lot of interesting stuff because the bonds are able to move and shift. And so you can move in this energy world. Alright, so the next thing we're going to talk about, we've got a lot to say about covalent compounds. This one's going to be longer than the ionic video, just to warn you. There's a reason I broke them up. And then this is the reason, this part. Because the ionic, I could do 2 of those, make a somewhat normal size length video. This one's going to be longer all by itself. So, we've got 2 types of bonds that we deal with. We have polar, which is the result of, so there's electrons being shared, but maybe they're not being shared equally. Maybe one side's hogging the electrons a little more than the other. Kind of like people don't always share blankets equally. So one person ends up cold, one person ends up hot. Well, if you don't share electrons equally, one side ends up pulling the electrons towards them more. They end up partially negative. The other side ends up partially positive, and so you have kind of like a negative and positive pole. Not like ions, not full plus and minus, but like, maybe a third plus and a third minus. And so you get poles. So it's called polar. And so that's the result of unequal electron sharing. Now your book has an interesting name for the other one. I'm going to use what I've seen to be the standard name everywhere else. Okay? So you've got polar, and also this just works better. And you've got non-polar, right? It's like you got winners and you got non-winners or whatever, Your book's like, oh, we got another name for them. They're called losers. But it calls it, your book says pure, a pure bond. I've never seen that before. So I'm used to polar and non-polar. If you look at any other source in the internet, you're going to see polar and non-polar. So I'm going to stick with it. But be aware that your book says pure. It also feels a little bit weird to be like, oh, this is a pure covalent bond. And this one over here, well, this is impure. It's, whatever that might mean. So, I think polar and non-polar is a much better way to break it up, even though it's just different language for the exact same thing. And so if polar is unequal electron sharing, what's going to be the opposite of that? Well, it's going to be equal electron sharing. Alright? So, how do we know what we're dealing with here? How do we know what a bond is going to be? Well, before we get into that, let's talk about electronegativity. Oops, which I like to abbreviate as EN because it's a long word, right? There's a shorthand for every long word in this class. You've caught on to that by now, I'm sure. And so electronegativity is the measure of, so we have these shared electrons, and you might think that it's like a peaceful, like, oh, both sides are sharing, and really what it is a game of tug of war. They are sharing because one side is not able to take the electrons from the other. So they are both fighting over the electrons. One side might be better at taking the electrons, or maybe they're equal. So you got non-polar and you got polar. Like it's winning, but it hasn't done the ionic thing where it's just taken the electrons. But essentially it's like a game of tug of war. And electronegativity is how strong of a competitor at that game of tug of war is the atom. How strong is the attraction between that nucleus and the shared electrons? So it's the strength of attraction between an atom and shared electrons. So it's a little bit different than electron affinity, where it was taking, what's the energy associated with taking an electron on. This is how much pull is it going to have on shared electrons. So it's a little bit different. In terms of trends on the periodic table, though, very similar. So when you look at our periodic table, as we go left to right, electronegativity goes up. Because as atoms get smaller, they're going to have more pull and electrons around them. You're going to have less electron screening. You're going to have less other electrons interfering with the shared electrons, right? The closer the valence shell is, the more pull there's going to be. Now, noble gases just don't compete. Why would they share electrons, right? So they're out. So when I say to the left and then up, that means that fluorine is the most electronegative element, and that francium is the least, because that would be the most to the left and down. We add one more element, it'll bump francium, but for now francium is the least electronegative element, fluorine is the most electronegative element. They both begin with F, and that has never messed a student up in my entire career. So, to be clear, if we have increasing electronegativity, that's an increase in attraction. So fluorine is the tug-of-war champion, okay? It's going to be pulling on those electrons harder than any other element because it's in the top right. Metals tend to have very, very low electronegativities because they tend not to really share electrons. It's very easy for them to lose the game of tug-of-war completely. The other team is off having a pizza party with all the electrons, and francium is just left sitting in the mud. Nothing, no shred of dignity. Completely, ultimate victory was achieved on francium in the game of tug-of-war. Like they probably lost some fingers or something along the way. Like tug-of-war can get very brutal if you didn't know. Like that happens. And francium can tell you all about it apparently. So the periodic table trends are a lot like what we've seen before, for basically all the same reasons. If you go left on a row, you get an increase in electronegativity. And if you go up on a column, you get an increase in electronegativity. And so when you go up and to the right, because again, the noble gases don't compete, fluorine is top dog. When you go all the way down to the left, you get the weakest element, which is francium. Okay? Whenever I teach a lab class, someone always feels the need to make a France joke in there. And I don't know why that was the element that got named francium exactly, but it's very unfortunate for all of the pride of the French people that happened. All right, so I'm just going to talk about general trends. Your book is going to lay out the exact electronegativity values, the whole scale and everything. And then they're going to say like, oh, if there's a difference between the two elements of, say, 0.4, then it's no longer non-polar, or in that case, pure. It's a polar, and if it goes beyond, I don't know, it's like 1.5 or something like that, then it becomes ionic. In reality, I've taught from a number of different textbooks. Those values shift depending on what book you're talking about, what author. So I don't really emphasize the numbers. Now the homework might, so just be aware of that. I'm going to try to keep it out of the quiz as much as I can. I'll try to make sure it just kind of falls in line with the general trends, which I'm going to talk about. I'd rather you build instincts than just memorize numbers, okay? So here, I'm going to get a fresh piece of paper. Here is the situation in general. There's always the exceptions that blow up any sort of general trends, but this is general chemistry, right? So I guess we call it in general chemistry. Two atoms of the same element is going to equal nonpolar. Now think about that for a second. Does that make sense? Would two atoms of the same element share electrons equally? Well, yeah, they're going to have the same electronegativity, right? So for example, a chlorine and a chlorine. Those are both very electronegative, but that's just a top-notch, championship level game of tug of war right there, but both sides are pulling equally hard. The rope is not moving, it is holding solid because they are ultimately completely evenly matched. And you could have something like hydrogen and hydrogen. So that bond I showed earlier for H2, that would be a nonpolar bond. And so what we get, the term is delta electronegativity, so it's just one minus the other, is going to equal 0. So it's nonpolar. So that's general. And then oftentimes you'll see your book definition, it falls away from that, but generally carbon and hydrogen are considered nonpolar bonds as well. Your book is going to say no, so I'm not going to write it down. But in the future, if you take organic chemistry, like those are typically considered nonpolar bonds as well. And there's a lot of those bonds in organic chemistry, believe me. A lot of carbon and hydrogen bonds. So, what other situations do we have? Well, if we have two mismatched, two atoms of the same element that are both nonmetals. I forgot to mention that before. If you have two metals, you get a metallic bond, which we're not talking about right now. Two mismatched nonmetals is going to equal polar. So for example, carbon and chlorine. We're not drawing bonds yet. Even though I drew one earlier, we're not drawing them yet. That'll be the next video. These have mismatched electronegativity. So if we pull up our periodic table, chlorine is to the right, which has a bigger effect than being down. And you can look up the numbers in the table as well. And you see chlorine is more electronegative than carbon. Electrons are going to shade towards chlorine more. So carbon is going to be slightly positive in this bond. Chlorine is going to be slightly negative because it's hogging the electrons. Chlorine's out in the cold. It's not good as much as a blanket. Chlorine is nice and toasty. All right. What else could we have? Well, we could have something like nitrogen and fluorine, etc. Any sort of mismatch in nonmetals, you get a polar bond. And so what you have is a difference in electronegativity that does not equal 0. It's more than 0, and it's more than whatever the book says. So what's left? Well, what if you have, say, a metal and a nonmetal? What does that equal? Ionic. In that case, you got your metal, you got your nonmetal. They're going to share electrons? No, nonmetal. Almost always going to take them away. Very low electronegativity and very high electronegativity compared to a metal for a nonmetal. And so we've talked about some examples, but NaCl, magnesium and oxygen, so on and so forth. And what you get is a delta difference in electronegativity that is large. Okay? You get the world's fastest game in tug of war. This is like the warm-up match. Like college football teams tend to play some like a little college nearby early in the season to get like practice and sell tickets for an easy game. Every now and again that little team wins, and that's amazing, but 99 out of 100 times it doesn't happen. 99 out of 100 times just taken. So that's what we have here. This is like Ohio State, and then I don't know, Ohio Valley Technical College or something. I don't know who they play. I can make a bunch of people mad and say Michigan, but that's not where I'm going with that. But anyway, so you get a large mismatch in electronegativities. You don't get shared electrons. That's the takeaway there. So this is how you can tell if you have a nonpolar or polar bond. And then just to remind you that electronegativity factors into the ionic stuff too. So why aren't they sharing electrons? It's just not an even match. Both sides are always pulling on the electrons. Metals just can't really hold on. And then, you know, if you have chlorine and chlorine, you got a strong match. You got hydrogen and hydrogen, not as strong, but they're still equally matched. You get carbon and chlorine, oh, you're going to sneak it towards the chlorine. Nitrogen and fluorine, oh, it's going to sneak towards the fluorine, right? Because nothing's beating fluorine. You could have two fluorines, by the way. They could be in a bond, in which case you get nonpolar, but fluorine with anything else, probably going to be polar. All right, so what else can we talk about? What else is there to talk about with covalent molecules? Well, in the last video we talked about naming ionic compounds. So now let's talk about naming these guys. Let's talk about naming the covalent compounds. So the nomenclature, which again is just a fancy way of giving me job security, because it just means naming. It's just a system of naming. And so first off, we're going to use the same prefixes as hydrates. We're going to use them a lot more though. So we're going to use those prefixes. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is, I know you've already memorized them all, but I'm going to write them out anyway. Hepta, almost like a HEPA filter, but not quite. 8 is octa, 9 is nona, 10 is deca, oops, deca, and it actually keeps going from there. And you have undeca and dodeca, and then it just keeps going and going and going. All right, so those are the only ones you have to know. All right, so let's just look at an example here. All nonmetals, covalent compound. You might know this as water, but if you use the naming system, it is known as dihydrogen monoxide. Good old, dihydrogen monoxide kills so many people every year. You might know it as drowning or pneumonia, but that's dihydrogen monoxide overdosing. That's what that is. Very dangerous chemical. You gotta watch out for those chemicals. Alright, yeah, or, just water. There's a reason we just call it water, even chemists, because guess what's shorter, right? It's just water, okay? So, you have a prefix for the number of them, because you can have H2O, you can have H2O2, I mean, you can have just different compounds with different formulas. It's not like ionic compounds where it's a set formula because of the ion charges. Now we can kind of get things get a little bit more creative in terms of structure and whatnot. We'll get to that later in this chapter, but that means we're going to use prefixes on everything with one exception, which we'll talk about in a minute. So you have a prefix, and then you have the name of the less electronegative element. And then after that, you have a prefix and the more electronegative element. So hydrogen is less electronegative than oxygen. That's why we write it first in the formula, but it's also why we write it first in the name. And then what else did we do? Look at that. Does that look familiar? We changed the ending to "ide." So if you're seeing these prefixes, and it's not for a water hydration, if you're seeing these prefixes outside of that, they're just in the name, you've got a covalent compound. That's how you know the covalent compound from the name. From the formula, you see metals and you see all nonmetals, excuse me, you know it's covalent in my class. I'm not going to say it's that way in reality, but more often than not, that's the case. So that's what we'll stick to. All right, so there is one exception though that you got to keep in mind. we don't use the mono prefix on the first element. So you'll never see mono here. We just say the name of the element if there's just one. So for example, if you look at CO2, this is known as just carbon dioxide. So it's not monocarbon dioxide, just carbon dioxide. So there's no mono for just one of those. But if you had something like CO, it's still carbon, but now it's monoxide. Which, by the way, we don't say monooxide. That would be ridiculous. So heads up on that. You saw it earlier too. So we use it on the second element, but we don't use it on the first. So it can show up here. So that's the only place you'll ever see monos. All right. So let's just kind of emphasize a couple points here. Some stuff I really want to make sure you remember. So do not forget this. If you've got ionic, it has a different naming formula than covalent. So if you're naming a compound, first thing I do is figure out, is it ionic or covalent? Because if it's covalent, you're using prefixes. If it's ionic, you're not. So the other thing too is if you got a name and you need to write the formula, covalent's just going to tell you what to write. You just go, oh, carbon monoxide, one carbon, one oxygen, and you're done. Ionic, you get something like, aluminum chloride, and you go, it's not one aluminum, one chlorine. No. It ends up being one aluminum and three chlorines because of the charges, 3 chloride anions. So how do we know it's ionic? Well, if you see a metal and a nonmetal, or those polyatomic ions, if those show up, you got yourself an ionic compound. No prefixes. Remember that. So we talked about the whole naming system before in the last video. That was the whole story on ionic. Covalent, all nonmetals, no polyatomic ions, all that stuff. Yes to the prefixes. So, you do not need to know those prefixes to name an ionic compound, but you do for covalent. You're going to have to know how to name both, so you do need to know them, but keep that in mind. So, the last thing we're going to talk about here is naming acids. It's always a little bit weird for me when I want to talk about this. Your book drops it now, so I'll just go with it. Sometimes I wait till we're doing solutions, but that would be like the whole end of the semester, so we'll just get to it now. So here's the quick, expedient definition of what an acid is. So acids are going to be substances that release H+ ions when dissolved in water. Okay, so that's it. That's what they do. There's different types of acids. We'll have a whole bunch of time to talk about those later. But just for now when you're naming stuff. And so it means that what you have are things that have H's in them. And so, for example, HCl, typically it's a gas. You really don't want to mess with it as a gas. You don't want to mess with it once it's dissolved in water either, because then it's a strong acid. But if I had to choose which one I'm working with, I'll take the one that stays in the beaker without a lid. Thank you very much. So you add it to water and you get H+, they separate, which is aqueous, means it's dissolved in water. And you get the chloride anion, which is also, aqueous and dissolved in water. So we have kind of two ways of naming stuff. So if you think about this anion that's left after the H+ leaves, well, if it's monatomic, we go with the following name. Oops, sorry, not hydrogen. Hydro blank ic acid. So for example, HCl, we dissolve that in water. It's going to be hydro, And then we have the chloride anion left, so it's chloric. So we change the ending to ic acid. So we keep changing the endings on these things, I know. Alright. If we have a polyatomic anion, so something that's like a polyatomic ion that's left over after the H pluses pop off, then it depends if it ends in 8 or it depends if it ends in ite. 8 is going to equal blank ic acid, so no hydro. Ite is going to be blank us, OUS acid. So for example, if you remember, NO3 minus is nitrate. So HNO3, which by the way, it has to be dissolved in water to be an acid, otherwise it's like a gas or something, and it's not an acid. This is going to be nitric acid. So the 8 changes to an ic ending, and then we just put acid on the end. Now if we have NO2 minus, this is nitrite. This is also on your list. So if we have HNO2, and it's dissolved in water, this is nitrous acid. Got a little squeeze in the corner there. So that's how we name our acids. So you got to look and say, well, what kind of ion is left behind? So if I dissolve this in water, I get a nitrate and an H+. They separate. I get over here, I look at this, I'm like, oh, that's the nitrite anion, that's nitrous acid. And you'll notice that, like, different names, right? So there's no repeat. The monatomics always have the hydro in front. So if I say hydrochloric acid, I know it's going to be this formula. So it's 1 to 1. These are very similar ions. They both have the same root, so we have to give them different endings, nitric and nitrous acids. Alright, so that is everything for this section. So next we're going to talk about drawing these molecules, these ionic compounds, with their Lewis structures. So we're going to, which basically is a way of mapping where the valence shells are going on paper. And that's what we're going to do next.